This is my ball balancing robot BAB, which stands for ball and beam. The sole purpose of BAB is to balance this ball at whatever set point I choose. This setup is meant to be an educational tool for control systems, specifically the PID controller. In this video, I'll be explaining the PID controller mathematically, along with applying it to the robot BAB and tuning it in the process, with the goal of giving you an intuitive understanding so you can apply it and tune your system. I'm going to make this video quite straightforward, so it is not too math intensive. However, if you do have some engineering or STEM experience, maybe you've done 2 years of engineering, it will certainly help you solidify some of the knowledge presented in this video. The topics shown on the screen here are some of the things that we'll be discussing, and having some prior knowledge on these will certainly help you understand the PID controller. The purpose of a PID controller, like every other controller, is to control a plant or system to a desired set point set by an operator. The architecture described takes the form of a closed-loop controller as seen from the very simple block diagram. In this case, R represents the desired set point, E is the error between the set point and the current measurement, U is the control input, and C is the system output. Now, in the case of our system, say we have a beam that's 20 centimeters long and we want the ball to balance in the center. We could set the set point to be 10 centimeters. Now, the error signal that's getting fed into the PID controller is the difference between the potentiometer readings and the set point, since these readings tell us where the ball is positioned on the beam. Based on this error signal, the PID will compute some output, which is directly writing to the servo motor that adjusts the angle of the servo crank. Once adjusted, it's directly linked to the beam, which causes the beam to change an angle, in turn making the ball move. With an understanding of our control problem, let's see how the PID controller actually works. PID is an acronym that represents the three components that make up the controller: the proportional, integral, and derivative components. The mathematical formulation of the PID controller can be seen here. As the name suggests, the proportional component is just a multiplication of the error, the integral component is an integration of the error, and the derivative component is the derivative of the error over time. I'm going to break down what each of these components actually do so you have some intuition as to how to tune your respective K gains. Starting off with the simplest component, Kp is the tuning parameter responsible for the speed of the response. This means that if we increase Kp, the ball will get to the set point faster, in theory. This is intuitive since you're simply multiplying the error by some scaling factor Kp. I'm going to illustrate the power of Kp using a traditional step response. The green line represents the set point and the blue line is the system response, which is the ball's position. As you can see here, this system is already tuned. However, let's assume we want to increase the speed of the response, both the rise time and the settling time. Then we'd crank up the Kp, which is represented by this red system response. When comparing both plots, we see that the settling time is less on the red curve with the increased Kp than the blue curve with the original Kp by 4 seconds. In addition, the rise time is much faster on the red curve. However, the trade-off being increased overshoot. Now that you have an understanding of what Kp does, let's apply it to BAB. Assuming all of the gains are set to 0 and we add some Kp to the system, we are looking for a step response that looks something like the purple curve shown here. If the system is in fact controllable, you will be able to reach this oscillatory state. Switching to the physical setup, we could tune Kp via serial communication between my computer and the Arduino Nano running the system. I got it on my first try because I knew which gain to use, but yeah, you will probably take some time to tune it. The second component I'll be getting into is the derivative gain. The derivative gain is responsible for dampening the response of the system, reducing the overshoot induced by Kp. Going off of the previous plot we had when reducing the rise time and settling time with Kp, we could reduce the overshoot using Kd. Increasing Kd may yield something like the red curve shown here. As you can see, the overshoot of the blue curve is much larger than the overshoot of the red curve. To understand how this works, we have to look at the error plot over time, which is represented by this purple curve here. Given the nature of the derivative, we're able to determine the rate of change of the error at the current timestamp. This means that we're able to see how fast the system is changing over time. Near the beginning of the response, we may get a slope that looks something like m1. And near the top of the response, you might get a slower rate of change that's represented by the m2 variable. Now, if we calculate the absolute value of the slope represented by m1 and m2, we could see that m1 is much larger than m2, meaning that the derivative component will have a larger effect on the overall PID output at m1 versus m2. This checks out since these components are actually negative, reducing the initial large overshoot that happened with the blue curve shown previously. So to summarize, based on the current rate of change, we're able to determine the speed of the response, and the derivative component will compensate for higher speeds by having more of an effect on the PID output, since there will be a larger rate of change. However, two things to look out for. One is that if you overdampen the system, you might get a very slow rise time. The second thing to consider is very noisy signals will be amplified by the derivative gain, given the nature of numerical differentiation. The updated response from BAB when adding KD should look something like this. As you can see, it's not quite there yet, but very close. Now back to the physical setup to tune the derivative gain. The final component to tune our system is the integral gain, which is responsible for eliminating the steady-state error of the system. Jumping straight into BAB's response, we can see that there is a difference between the set point and the steady-state value of the system. This is known as steady-state error. Now, the exact nature of where the steady-state error comes from lies in the system type and the dynamics. So you may not actually have any steady-state error depending on your system. However, BAB does have steady-state error. The steady-state error of your system can be calculated using something called the final volume theorem, which I won't be getting into, but I can show the formulation here. What the integral component does is accumulate the error over time, keeping sort of a memory of the system's response. This will account for any weird deviations, such as that yellow region shown previously, and compensates accordingly depending on Ki. If you want a more theoretical explanation, I recommend looking into the final value theorem along with what happens to a transfer function when you add an additional pole to the system, which is inevitably what's happening when you add an integration term. Now moving to the physical setup, the system did brick the first time I tried tuning it, so let's try that again. Now there is a deadband, meaning that the ball could be considered balanced once it's plus minus 1 centimeter within the set point. So the servo won't actually activate anymore once within the deadband. As you may have noticed, these small tweaks near the end are a consequence of the integration term. Alright, to recap the tuning process, first tune Kp until your system is oscillating, then add Kd until your system reaches a steady state, And third, add Ki until your steady state error is eliminated. Although the PID is old, it's used in practically every industry, so it's definitely worthwhile learning. I hope you've enjoyed this video and learned a thing or two about control systems. If you did enjoy it, please leave a like or comment, and be sure to subscribe if you want to see more content like this. Thank you very much for your attention.